so that we can talk about this, because this is going to be on your quiz tomorrow.
Yeah.
You have to be able to distinguish the Z's from the T's. Alejandra, did you have a question about that? Or are you good with distinguishing your Z's from your T's?
I think I'm just catching on setting up my stuff. I think I'm good, but I would like a refresher.
You're okay. So, okay.
Yes.
Just wondering, because that tends to be something that people have a question on. Let me bring up the slides for this lesson and show you, Jay, what's happening here. So 6.3, let me share the screen. Right here, 6.3. So as I said, 6.2 is about means, so is 6.3. So these are side notes here. Now this is going to play into the second part of our question. So the distribution of sample means, regardless of which one you're doing, will be nearly normal if the sample size is greater than or equal to 30. If it's less than 30, then the original variable should be normally distributed. Remember this bullet point. We're going to come back to that. This plays into this question. The original variable can have any distribution. It does not have to be normal, okay? So, but if it's not normal, you've got some constraints on it. So we've talked about that before. We've done this before. We have the Z's here. Okay, this is my 6.3, right? But you have your Z here. And this is your Z-score here. Okay, but there is a situation in which sometimes we have to use T's, okay? So this distribution here is, and I don't see it on this. Let me look back and see, because I don't see it on this slide. So maybe she hasn't. Let me see if that was actually 6.2. Because I know we should be doing, hold on, let me go back to, because that is not where I thought I was looking at. So let me go back to the modules and make sure, because yeah, we should be doing T distributions for this. If you're normal, then you're sample, but it should be a situation where, whoops, I'm in the wrong course. Let me check the modules here. Let me go back to courses, because I'm in the pre-calc. I was just doing a meeting for pre-calc, so I was in the pre-calc modules when I did this. There should be a slide on it that she gave you, where she said, so I will go over that with this. Yeah, 6.2 is applications of the normal. 6.3 is the central limit theorem for sample proportions. And then 6.3 is the central limit theorem for sample means. So let me pull down this PowerPoint. Because this is, oh, maybe she did she not get to? She must have done the T's. She has to have done the T's. But I don't see, let me check. Because she has to have done, it depends on whether you know sigma or not as well. which I'm just wondering if she actually, no, she doesn't mention that. That's very odd. Let me check something here because maybe we should have done T's in this, and she has these in both of these. I'm gonna check the book because there should be a T for that. Let me check something. Actually, let me go back to this. Hold on. Section 6.3. Hold on. Let me go, because that's weird. Okay. This is going to be central limit theorem for mean. Because I didn't get to the T's when I was doing it. So I haven't done it. And there should be a video on it. But that's weird. I don't see the, let me see, T distribution. Okay, this is 631. This is chi-square. Yeah, I'm not, this is strange. Okay, let me find the T's because there should be T's. You should have degrees of, there should be something with degrees of freedom and let me just do it, but I'm gonna have to find that because I don't know where that is right now. What this is gonna be is this. We're gonna have, we have a mean here. This is mu. The average weekly benefit is 272. Suppose that the benefits are normally distributed. This is your clue. These benefits, this population is normally distributed with a standard deviation of 43. So that's why this applies in this case, because this standard deviation is known here, okay? Normally we would use a T distribution for this, but our population is normal and our standard deviation of that whole group is 43. So this sigma is known, it's 43. A random sample of 15, that's my N, is chosen in Montana. What is the probability that the mean for this sample, that's my X bar, is greater than the US average, which is 299. Is the normal distribution appropriate? So let me answer the first part first. Yes, the normal distribution is appropriate because your population was normally distributed. If it had not been, you wouldn't have been able to do this. You would have had to use the T distribution for that. Okay. But we could because and it could be that that's coming in 6.4. I'm not sure. I don't remember right now. But here we're going to get this. We're going to get mu. I'm going to write my numbers down. So I have mu is equal to 272. Standard deviation is 43. N is 15. And the probability that X bar is greater than 299. So we're gonna have, so it's gonna look like this. Let me get the calculator out so we can compute the z-score, which I don't have my calculator open, so let me open it. This is going to be, let me stop sharing because I've got too much stuff open and pull the calculator out of this. So you have your z-score. So you should have 299 minus 272 over 43 divided by the square root of 15. Let's try that and see what we get. So we end up with, let me share the screen again. We have this is, let me move some of this out of the way. We have 272. I'm sorry, yeah, it's 299 minus 272. Don't forget your parenthesis, that can cause issues. Sigma here is 43 divided by the square root of 15. Okay, so then this gives us our z-score, which is positive 2.43. Remember, z-scores generally go to 2. If you went to 4, that's okay. But I think on her key, she went to 2. 2.43 should be your z-score. Now, you're looking at, here's 2.43. Let me just do something here. I'm going to draw on the screen. Let me annotate this. So I have let me see, where is my, this is my, here's my curve here. This is going to be my middle score. So this is going to be 242, 242, or 2, what was it, 2, did I put? No, this is 272, sorry, 272. This is going to be 299. So this is going to be 299 is going to be somewhere over here. And I want to be larger than 299. So I want to be over here, right? So I got my z-score, which, did you get the same z-score that I got?
Oh yeah, the 2.4318.
Okay.
Yeah.
So, okay. So I'm looking for this, right? So now, this is going to be, we're going to put that in the calculator. So we're going to have second, use the mouse. Second, quit from there. So this is going to be, okay. So we have second distribution. Second distribution, we're going to have 2.43. This is going to be normal CDF. This is going to be 2.43. My upper is positive infinity, my mu is 0, my standard deviation is 1, and I'm gonna paste it. And I end up with 0.0075 for my answer. Remember that when you're plugging in the z-score, you don't change the mu and the sigma because you're plugging in the z's. So don't change mu and sigma for that when you do that. Those are 0 and 1.
Okay.
So that's where that came from. Does that help or?
Yeah, I think what I was missing was I wasn't doing the standard deviation divided by the n.
Whenever you have, now here's a little trick. Sometimes this helps students. If it helps you, use it. If it doesn't, that's okay too. But if you always think of the formula as z or t when we get there, I don't think we're there yet. Z is equal to x bar minus mu over sigma divided by the square root of n. If you always think of the formula as being this way, let me show you something. When I'm doing an individual value, right? When I ask you, what is the probability that an individual has an IQ higher than 100? Or what is the probability that an individual CEO is more than 30 years old? If I have an individual down here versus a sample, if this is an individual, then for individuals, n is 1, right? Now, why do I bring that up? Well, if that's an individual score, then this becomes z, this is z is equal to x bar minus mu, and then this part becomes the sigma down here stays sigma, but the square root of 1 is 1, right? So this just becomes x bar minus mu over sigma. So if it helps you to remember it that way, you can. You can always think of using the n if you'd like. And if it's an individual, it's just going to be 1. So it's going to resolve to this every time you do it.
Okay, yeah, that makes sense.
Because of that. But, and if you're doing a sample of 15 or 30 or whatever, but if your sample is smaller than 30, you have to make sure that your distribution is normal in order for this to apply. Otherwise, as I said, we have to use the t-score.
Yeah.
Alejandro, did you have a question about something?
More so about 7.1, but
7.1, okay.
This is good refresher.
So you're doing the confidence intervals. Okay. Let me answer her question. Did you have another question about this?
Oh no, that helps me like understand how to do the other ones too now.
Okay. You're welcome to stay and I'll be here. So you're welcome to continue to sit in with us if you like.
Okay, yeah, because I was a little confused on 7.1 too.
Yeah, I can imagine. We don't have I will be here again tomorrow morning before the exam or the quiz, I should say. So I'll be here running a tutoring session early in the morning before the class on campus for those of you who might be in the hybrid class. Did you see my message earlier? Alejandra,
Yes.
did you
Was
get
it
it?
at 8 a.m.?
I asked Professor Nick Dell to send it as an announcement also,
Mhm.
just to make sure.
Yep, I got it.
So,
Thank you.
I'm sure everybody and their friends got evangelized appropriately, let's hope. Let me switch to 7.1 because I need to download that. And this is where hold on, let me switch. How far did you get in 7.1, Alejandro?
I'm currently on number 6.
Oh,
I think
good.
there's about 4 questions.
You're making it work, huh? Let me see where this is. Confidence intervals for the mean standard deviation known or a K bigger than 30. All right. So yeah, these are going to deal, 7.1 is going to deal with the Z-scores. Okay. 7.1 is going to deal with the Z's because the standard deviation is known and N is bigger than 30. Number 6, you said. Okay. So are you on number 7 or are you still on number 6 somewhere?
I'm still number 6.
Okay, no
I
problem.
just finished number 5. I noticed I had to do the 1 minus, right? Like for example, on number 5, 1 minus the decimal of 95%.
The average, oh, to get
Mhm.
the number, you mean?
Yes.
To
And
get
then it
the,
looks when I go back, I have to go to inverse norm, right? And then I do 1 minus again.
okay, so let me just clarify.
Okay.
Before we put the whole confidence interval together, and I'll show you that, but let me clarify this. So before we get too far into it, because this may trip you up, if this doesn't answer your question, let me know. And then we'll work with the question, but let me try this. Let me go ahead and share the screen again and go to a whiteboard here. So just a couple of points of clarification for chapter 7. What we're doing in chapter 7 is creating what we call a confidence interval, okay? And when we have a confidence interval, they are estimates, okay? Now there's 2 ways to estimate something. I can estimate something with a single number, or I can estimate something with a range. If somebody says, oh, well, I'm going to estimate that Shauna has been at Cerritos College for between 10 and 15 years. That's an interval estimate. It's a range. Or you could say, I estimate that Shauna has been an employee at Cerritos College for 15 years. That's what we call a point estimate or a single number. So what we have when we have a confidence interval, whether we're doing it with a proportion or mean or whatever, is we have 2 bounds. We have a bound that forms the interval, and we have this middle number that could be a mean, it could be a proportion. In this case, it's a mean, okay? In this section, it's a mean. So it's now we're trying to estimate the population parameter. So essentially what's happening here is we're using samples, okay? We're using sample data to estimate population parameters. Okay, that's what we're doing. That's how we're doing it. And the confidence interval here is going to have X bar in the middle of it. Okay, So if I'm asking you for, let's say, let's use a percent that we don't use, just so I can show you this and it won't be something that you memorize. Let's say I wanted to form the 92. Let's do 92%. 92% confidence interval, okay? What this percentage gives me is the percentage of the area under the curve that covers my boundaries, okay? So if I'm telling you that I'm doing the 92% confidence interval, then I'm talking about this region being this region being 92 in here. Talking about that. So the first point I want to make, and this should help you, Alejandra, is that my alpha, which we'll come back to this, my alpha, which is my area in both tails, my alpha is equal to 1 minus the confidence level. Always. Alpha is 1 minus the confidence level. So if this is 92 here, or 95 or whatever it is, okay, then this amount, this is 92, let's say, right? Then I have area in either tail, and those are symmetric. So my tail area here, my tail area is going to be 1 minus 0.92. Now, I'm going to show you something. If you haven't seen it, it's in the lesson. But you should also, this is where your handouts are going to come in handy, because she gives you the format for finding the confidence coefficients. All right. So 0.08, and then you divide that by 2. So 0.08 divided by 2 is 0.04. Questions about this so far? Is that
No.
you're okay?
Yes.
So this is 0.04 on this end here, and on this end here, 0.04. Okay. So when now this goes back to the stuff that we learned in chapter 3, and then again at the beginning of this chapter. When we do confidence coefficients, and students get tripped up on this every semester too, is there's always 2 numbers, because we learned that symmetrical, there's 2 numbers. There's always, why don't we use the negative number? Well, we don't use the negative number because we're looking for this confidence coefficient down here. We're looking for the positive confidence coefficient, because that's part of the formula. So you want to go with everything to the left, and we know, to answer your question from earlier, that that's inverse norm. So in this case, this is going to be my, what we call my confidence coefficient, or sometimes I think she calls it just the Z, but it's just the confidence coefficient. This is inverse norm of, here it's going to be 1 minus, and this is the general form. This is 1 minus alpha, I'm going to use A, 1 minus alpha divided by 2. Okay, that's going to be my confidence coefficient, because you take Alpha divided by 2 is 0.04. 1 minus 0.04 is 0.96, which is what 0.92 plus 0.04 is. Or you can do it in 2 steps and add. But that's how you do this. So if you go back and say, if you go back to the homework here, and it says, in a recent survey of 35 ninth grade students, the mean number of hours per week that they played video games was 16.6. The standard deviation for the population was 2.8. Okay. So what is my 35 here?
Sample size?
That's my N, right? Which mean is the 16.6? Which mean is it?
Sample mean?
That's right, because it says they. Who's they? This is my study of 35. So this is my X bar, okay? This is the middle of my, right. And it says the standard deviation of the population, this is my sigma, was 2.8. So I know I'm using a z-score here. Now for part A, what is the point estimate signifying here? What is the point estimate?
Is this looking for a percentage?
Remember, what are we estimating? What are we estimating here?
Oh, the interval? Or
We're
point?
estimating the confidence interval for what? Here's a hint, look at part C, or even part B. Confidence interval for
the Z alpha.
for the mean, right?
Mhm.
So we're estimating the mean here, right? And there's 2 ways to estimate the mean, with the confidence interval or with the single value, right? The single value is called the point estimate. Now, what is the best point estimate? What is the best single number estimate for the population mean? What is it?
16.6.
Right, that's exactly right. So the answer to part A, and this is the reason, the best point estimate for, remember, we're doing point estimates for the population, right? The best point estimate for the population parameters are the sample statistics. So if you have a population mean, the best point estimate for the population mean is the sample mean.
Okay.
Okay, so the part A is 16.6. Now, if I want to find the 95% confidence interval of the mean, then let me go and show you. Let me bring up the slide so we can look at it. Now, 95, she gave you, because 95, we used 95 a bunch of times. And you should find that that's 1.96, if I'm not mistaken.
From the previous question.
Let me go and look at the, I think her Slides are mislabeled here. I don't think the slides are wrong. I think the sections are mislabeled. Let me take a look and find the actual slides that I'm supposed to be looking at, because hold on. Let me go to bring it up here and say look for the file. Open it. This is going to be the central limit. Actually, not central limit. This is going to be confidence interval for means. Okay, I don't have that up right now, so let me look. 6.3, let me see. 7.2 confidence intervals for the mean. No, I need 7.1 here. Let me look at 7.1. So if I look at 7.1, oh, go away. Let me see. 4, 3, 4, 4, 8. Here it is. There's the PowerPoint that I was looking for. All right, let's take a look here. So we have there's my chart. We were looking for your chart. There they are, right? So here's a picture of what I just gave you. This is 95%. So my alpha is 5% because it's 1 minus 95. 0.95, which is 0.05. You divide that by 2. So here's your distribution. And here's your procedures on slide number 10. Okay. Confidence interval. She gives you some confidence coefficient. Okay. You have there's your formula. Okay. X bar minus Z of alpha 2 sigma over the square root of n. Before you look at the formula and go, oh my goodness, this left half is the same as this right half, except that on the left side you're subtracting it, and on the right side you're adding it. Okay. You get the Z from your calculator, and then you divide sigma over square root of n. So give me a second. So this term is the same. So when you go to do your homework over here, right here, the first one is the 95, the second one is the 99. The only thing that's changing is your Z-score. Okay?
Okay.
Does that help?
Yes. So that's all we do is, let me see, check the answer.
Well, if it's raw data, you'll have to put in the data and get your sigma from the calculator.
Okay.
and count your ends. But again, your calculator will do that. But that's essentially, yes, that's all you're going to be doing in that section for that. Mhm.
Do you mind if we walk through it just to confirm? I think I'm gonna.
Sure.
need
Are
to know
you
that-
are you doing
Yeah.
B? Are you not agreeing with B?
No,
Or-
I agree with B. So I'm gonna get the 1.96.
Uh-huh. So on number 6, you have N is 35, right?
Mm-hmm.
I'm gonna write this out. Mean number of hours was 16.6. And you have the standard deviation of the population was 2.8,
Mm-hmm.
right? You want to find, so A was the point estimate. B was the 95% interval, 95. C was the 99. And which is larger, explain. All right, so if we go here, and once again, we, the first thing we said was so this is problem 6 from 7.1, okay? The first part of this was, what is the best point estimate, right?
Mm-hmm.
And the best point estimate for mu, which is the population mean, the best point estimate, the best single value
Mm-hmm.
estimate, that's what that means when you see that. A point
Mhm.
estimate is a single value. The best single value estimate for the population mean is the sample mean. And we discussed earlier that that was
Mm-hmm.
16.6. I think we're good there.
Yes,
Okay.
that's given.
That forms that's going to be the middle of your confidence interval formula. Okay. Because your confidence interval formula is this. Let me remind you. You'll find this on the slide. We'll go back. You have mu in the middle, right?
Mm-hmm.
You have X bar, okay? So that is your point estimate. That's this 16.6 right here. Plus or, so this is plus if it's on this side. Sometimes we write it as plus or minus, but I'll write it as plus right now. Here's my Z. We write this with a subscript Z alpha 2, which is just a way of saying that it's related to my confidence interval. And this is sigma over the square root of n. Now, this piece is the same. It looks intimidating, but this piece is the same as my other, the other side of it. So this is just X bar minus Z sub alpha 2 times sigma over the square root of n. This is the same thing on both sides. So what you can do if you're doing this with a calculator and you're doing this by hand is I would say find your z-score. So if I was going to construct this, I would do the following. I would say step 1, is find the confidence coefficient. Okay, step 2 would be to calculate what we call the error, which is you're going to calculate the z portion. You're going to calculate this here. You're going to calculate that. So you're going to calculate what we call the error term. And then you're going to just add or subtract to find the boundaries of your interval. Are you not getting what the key is getting? Is that the problem? Or you're just not sure how to put it together?
Yeah, I wasn't sure how to put it together, but
that's
I think
fine.
yeah.
So here, okay, so based on what we know, we know that, okay, so let's get our Z. Z, because we're doing 95%, okay? So she gave it to you, but let's say she didn't give it to you, okay? We know what this is, so let's do this once. So here's the distribution. You do not have to draw this, but it is helpful when you're learning it to do so. This is 95 in the middle here. This is 95. And the pattern, for reasons that I showed you earlier, my alpha is 1 minus the confidence level. So based on what I showed before, alpha is equal to 1 minus 0.95, which is 0.05. Okay, that's the area in both tails together. So this is the area in both tails together. You need the area in one tail. So you're going to take alpha and divide it by 2. This is equal to 0.05 divided by 2. You do not have to do all this math. You can put this in the calculator without doing it, but this is how she got the number that she got. This is 0.025, and this is 0.025 over here. Questions so far?
I think I just might have an extra step here. Earlier, I did 1 minus 0.95 equals 0.05, and then I did the inverse.
So your Z is going to be, that's the next inverse.
Oh, okay.
This is good. Your format is always this: 1 minus alpha divided by 2. Okay. You don't have to do any of this arithmetic except 1 minus alpha. I just did it because the PowerPoint has it. And every semester students ask me where it comes from. So there it is. This is inverse norm. This is going to be 1 minus. This is going to be alpha. Remember, your alpha is not 95. Your alpha is 0.05. That step you do have to do. You have to do this first step. This first step, you have to do it. This one. You have to do that because I have to know what alpha is. Okay, so this is 1 minus. This is going to be 0.05 divided by 2. Now, if you put this in your calculator, okay, we're going to switch screens. So I'm going to share the calculator here. This is going to be, second quit. And I'm going to go second distribution, inverse norm, number 3. This is going to be 1 minus, and use the big minus, not the toggle minus, 0.05 divided by 2. You want this to be 0 and 1 because you want the z-score. So go down here, paste it in. This is this amount. There it is. Take this to 2 places. This is 1.96. Okay. Questions here?
No.
Okay, good. So now this is going to be, this is going to equal 1.96. Okay. Now, what we're going to do is create the confidence interval now. Now, I would suggest that the next thing you do is calculate the error separately. My error is that part of the formula that looks like this. That's going to be z alpha over 2, and we know what that is because we just calculated it. Okay, we know what the z is. This is going to be sigma over the square root of n. Okay, that's going to be my error term. You're going to take this to 4 decimal places. This calculation generally goes to 4 decimal places. Okay, the z normally goes to 2. If you took it to 4, don't worry, she's not going to quibble, but this calculation goes to 4. So here, this error term is going to be, we're going to have 1.96 times my sigma. Remember sigma, I know it seems like a lifetime ago, but that comes from the problem. Sigma is 43. And you're going to divide that by, you're going to divide this by the square root of your sample size, which is 15.
I'm sorry, Shauna, where do we get the 43 from?
Let's go back to here. I'm sorry, it's not 43. I was looking at, I think I was thinking about Jay's problem earlier.
Would
Good
it be
catch.
the 2.8?
This n is 35 in this problem.
Okay.
And the standard deviation is, yes, good catch. I was thinking about the other problem that we did earlier.
Oh, no worries. Okay.
The standard deviation is 2.8 here, and the sample size is 35. My mistake. So yeah, the standard deviation is 2.8, then the sample size is 35. So we have, I'm glad you caught that. So let's fix this. Let me fix this problem before I carry on with myself here. So here, this is going to be 1.96. And my standard deviation is 2.8. So I have I'm gonna make a parenthesis here. This is gonna be 2.8 divided by the square root of 35. More questions about this?
No.
Okay, everything is good here.
Thank you.
That looks better, no? Now that Shauna has the right numbers in the problem and is not doing, that can happen. You can start doing a problem from before, especially if they have multiple parts. So don't do what I did, okay? So there's my error term, okay? So let's put that in the calculator. We have, now remember, this is just a straight calculation. This isn't, oops, this isn't the inverse norm of anything. We already did that. So this, move this over here and share this, whoops, share the screen again. Go to the calculator. All right, so we have, all right. So this is gonna be second, let's see, we're going to do this. 1.96 times 2.8 divided by the square root of 35. 35. And then we're going to close this. And we're going to get 0.9276. Okay. So now, when we do our confidence interval, if you remember, I know it's been an eternity. Let me pull up the formula one more time. What we just calculated right now was this piece on the end, this z of alpha 2 times sigma over the square root of n. That's what we just calculated. So we're looking, we did this.
And then we just plug in.
And X bar for us is 16.6. This piece that I circled and this piece over here are exactly the same. Z alpha 2 sigma over the square root of n. Here we're subtracting it. Here we're adding it because we want a number smaller than the mean and we want a number larger than the mean, and our population mean will be between the two. Okay, so let's go back to our whiteboard here. And we have, this was 9276. Thank you. My personal assistant, 0.9276. All right, so now 9276. Okay, now we're going to form our intervals. So we're going to have this. We're going to say that's 16.6, which is my X bar, minus my error, which is 0.9276, is going to be less than mu, because remember we're estimating mu here, less than, because it's between them, 16.6 plus 0.9276. Okay. Any questions about how I formed that?
No.
No? Okay, so now it should just be a matter of doing the arithmetic. So let's do that. We have, let's go back to our calculator, because in this class, your calculator is your friend, for sure. So 16.6 minus 0.9276 you get 15.0724. I'll show you a little trick. If you don't know this trick, it might be worth knowing. You can go to second entry. Entry is above the enter key. So it's the blue. For me, it's blue. For you, it might be yellow or some other color, depending on your faceplate. But it's above the enter key in the right-hand corner. Second entry. It'll bring back the same thing you entered. You can go back and put in a plus sign and rather than retype everything if you want. You can also retype it, but sometimes the second entry key will save you some time. And there's my interval between 15.0724 and 16.9276. Okay. So my interval is between 15.0724 and 16.9276. So we have, if I go back one more time, this is going to be and I have to be leaving shortly, but I want to finish this. This is 15.0724, and that's less than mu, which is less than 16.9276. The only difference here with the other formula, with the next part, the only distinction you're going to have is that 1.96 is going to change. You're going to have a different inverse norm on part C because you're going to have 99. So this is going to be 0.01 here for part C. And so you're going to have 1 minus 0.01 divided by 2, which is going to give you a different Z for this piece.
Okay.
All right.
Thank you so much.
You're very welcome. Thank you both for
See
coming.
you tomorrow.
See you tomorrow. Take care.
Appreciate it.
You too. Thank you.
I'll send you guys the whiteboards so
Oh, yes.
you can review those. Okay.
Greatly appreciate
Just
it.
gonna
Thank you.
take, it's gonna take a little while for this
No worries.
recording to render, but once it renders, I'll be able to send it to you. So look for them later this evening.
Thank
All
you.
right.
Bye.
Thank you so much, guys.
All right. Take care. Bye-bye.
Bye now. I'm gonna do